So let's talk about how inverters function as voltage transformers. As we've been learning, both standalone and grid-tie systems tend to involve the flipping of voltage from DC to AC, as well as the stepping up of voltage that tends to be lower on many solar systems up to the 120 system that we find in household power in the United States. So transforming is something that's happening with voltage all around you all the time. Your laptop or computer, computers tend to have a supplementary transformer that steps voltage down because computers operate on much lower voltages than the 120 that comes out of your wall. And of course, everybody's seen these wall warts that also are dropping down voltages considerably from the 120 household to 9, 12, 5, 3.3, which a lot of small devices tend to use. Sometimes they are also turning it from AC to DC, and then other times they're just keeping it at AC. So let's take a look at how stepped up transformation works with these inverters that we see in our solar arrays. So transformers can increase or decrease voltage through the ratio of wire turns between the two halves of the transformer, known as the primary and the secondary. The primary is the side where the voltage is coming in. The secondary is the voltage that's going out to the load. So generally, transformers traditionally have been these iron cores that are often rectangular in nature. They're thick, they're 3D. And so what happens is they have two sets of wires that are coiled. And the coiling is what is important because Michael Faraday learned a long time ago that we can build up an alternating current magnetic field from one source of power that excites the electrons in a copper wire and deliver that power over. So what transformers do is that they take the power voltage of a primary, in the case of the example we're going to use today, 5.9 volts AC, and we're going to step it up to a higher voltage of theoretically about 9.8 volts. Let's see how that actually happens. So the transformer that we're using today takes a primary of 450 turns of the wire. So whatever the ratio of that number of turns is to that number of turns will act as a multiplier. So if we have more turns in the secondary, the voltage is going to go up. If we have less turns, then that's a step down, which is what's happening in these little adapters right here. But we're looking at stepping up today. So we see a ratio of our primary that we're going to have our incoming wires have 450 wraps around the core, whereas the secondary is going to have 750. That gives us a ratio of 750 over 450, which we can boil down to roughly 1.67. So whatever voltage comes in, this transformer will multiply that voltage by 1.67. So we would expect a 5.97 volt input will give a 9.8 volt output if it goes into a transformer that has this ratio. Now, warning, and you're going to see this in just a minute, some of this voltage that we predict we're going to get is going to be lost due to heat and the poor design of the transformer. This is a cheap transformer that is meant to be used for educational purposes, and thus it is much less efficient. So we're going to get close to this, but we're not going to hit it. There's no such thing as a perfect transformer. There's always going to be a little loss. The better the design, the less the loss. So let's take a look at what happens when we experiment with this voltage source on the input and we have a transformer with these ratios of turns between the secondary to the primary. So what we have here is our transformer, okay? And as we can see, this is an iron core with a primary coil of wires that has 450 turns and a secondary coil that has 750 turns. What I've also done is I've hooked up this transformer to an oscilloscope. And what this does is that it puts out the alternating current voltage as a waveform, which is what AC does. If this were DC, we would just simply see more or less a straight line. So let's take a look at what the voltage is at the primary. Okay, so I'm going to put a little multimeter here that is set to AC. It's set to reading alternating current. Whenever you use one of these multimeters to measure voltage, make sure you know whether you're looking at DC or at AC, and also try to set the appropriate voltage range. We're assuming that we're going to have less than 200 volts AC, and so I'm set for there. So I put the two leads of my multimeter across the primary, and we see pretty much 5.9 volts. Okay, try to get a little bit better there. So what we're going to do now is take a look at what happens in the change in the voltage and the waveform when we move our multimeter and our oscilloscope leads over to the secondary. So let's do that. So we carefully move these leads over to the secondary. So we've gone from the primary side. Now we're going to analyze what's happening at the secondary side. And look at the jump in the waveform. The literal size of the waveform has increased by about 2/3, and we predict thus the voltage should increase roughly by that amount, which we are predicting at, if not 9.8 volts, fairly close. 9.6 volts. It's kind of fluctuating, but still it's reasonably close. So we are going to get some losses. This is a very cheap design. Also note that these wires are kind of loose because they're meant to be able to be moved and changed around. So that's going to account for some of the loss. But as you can see, we have an increase in voltage from the initial 5.8, 5.9, and we've stepped up the voltage to about 9.6, which is close to our predicted ratio of increase based on the ratio of secondary turns of the transformer wires to the primary turns. Notice how these two coils of wire aren't actually touching. What is happening is we're building up an invisible electromagnetic field that is putting out a field of electromagnetic energy from the primary and is exciting the electrons in the copper wires here on the secondary. And as Michael Faraday found out in the 1800s, that the ratio of turns, if you have wrapped your coils correctly and we don't have any shorts out of electricity, will reflect the increase or decrease of voltage. So what we're going to do next is we're going to do one more experiment with this setup while we're here. I'm going to go ahead and temporarily shut off the power source that's going here, and I'm going to change the turns ratio here. So whereas we started out with 450 to 750, what do you think is going to happen if we move from 450 to 900 turns? So maybe stop the video for a second and think, and you may or may not need to take out a pencil and calculate what we think the voltage would be once we have changed the transformer's secondary winding from 750 to 900. So now we have a ratio of 900 to 450. Why don't you pause this video for a second and see if you can figure out what the expected voltage should be. So now we're going to get the power started again. All right, so we now are supplying power to the transformer. Once again, let's take a look at where we are at the primary. So we have a certain waveform that reflects about 5.9 volts. Okay, and we see that size of a wave. And let's go ahead and check the voltage once again. And we see that we've got 5.9 for the primary again. But now let's take a look at the secondary. And sure enough, it's a lot bigger power. As a matter of fact, in theory, if we had a perfect transformation, because this is the double number of turns, we should have the double the number of the voltage. So 5.9 would double to about 11.8. Now we didn't get that. We know there's going to be some losses, but that's reasonably close. And finally, let's take a look at the change in the waveform. And sure enough, it's gotten even bigger. So the waveform increases as in the depth or the height, if you want to say, of the wave according to the increase in the voltage. So in conclusion, what transformers can do is to step up or step down voltage according to the ratio of wire turns between the primary and the secondary. In most cases, we are trying to step up voltage with an inverter. So in all of the inverters that we are working with at CSAS, we have embedded, whether it is in one of those big inverters for the standalone or the microgrid inverters for the grid tie, these transformers in the device that have a primary and a secondary, with the secondary having considerably more windings to try to move that voltage up to either 120 in the case of the standalone or 240 in the case of the grid tie.